Okay, so today we'll start an important topic, beta and gamma function. So it is a part of calculus and real analysis, because topics of real analysis and calculus are overlapping. Okay, so we'll discuss beta and gamma function. Now the directly question comes in UPSC from this beta and gamma function, and it also helps in solving I would say very difficult integrals, or I would say improper integrals, which are not possible to solve using normal methods of integration. Okay, so first we understand what does beta function means. So beta BMN is a definite integral given by 0 to 1, integrating 0 to 1 from 0 to 1, x to the power m minus 1 minus x to the power n minus 1 dx for m greater than 0 and n greater than 0. Now this condition is given here, m greater than 0 and n greater than 0 for m less than 0 or n less than 0, this integral would not converge, it will be a divergent. Okay, so this condition is given that m is greater than 0 and n is greater than 0, and in the topic improper integral I will also teach you how to get this property. So that will be a topic for another day, but for now you understand that beta BMN, we write this as BMN is equal to integration from 0 to 1 x to the power m minus 1 minus x to the power n minus 1 dx. This is called beta function, is known as beta function. It is denoted by BMN and it is read as beta mn. Okay, so this is the basic definition of beta function. It will help us in solving very complex integrals which are not easily solved using simple techniques of integration which we have learned in our class 12th or even in our graduation. Okay, and there is another function, that is a gamma function. Okay, so that was beta function was a variable to multivariable function. It was in BMN, m and n were variable. Here in this case the variable is only one, n. So gamma n is 0 to infinity e to the power minus x to the power n minus 1 dx for n greater than 0. Here also we have taken n greater than 0 so that the above integral converges. See, it is written here, the integral 1, the earlier integral, is valid only for m greater than 0 and n greater than 0, and integral 2 is valid only for n greater than 0, because it is for these values for which m and n that the above integral are convergent. In fact, UPSC have asked direct question in improper integrals and given this integral and to find the value of n for which this integral converges. Okay, but we'll discuss this topic in the improper integral portion. Today we'll learn how to use this integral. Okay, so first thing is gamma 1 is equal to 1. Okay, to be able to show this, that gamma 1 is equal to 1. So we are given that it is very simple, that gamma n is 0 to infinity e to the power minus x to the power n minus 1 dx. Okay, so gamma 1 would be 0 to infinity e to the power minus x, and if we put x equal to n equal to 1, so we get x equal to x to the power 0, which is equal to 1. So simple, it is e to the power minus x dx. And solving this we get e to the power minus x, this is equal to 1. So this is general, this will not come in your examination most probably. So the more complex question would come but this is just to show that gamma 1 is equal to 1. Okay, moving ahead. Now this is a very important theorem, in fact very important property of gamma function, that is gamma n plus 1 is equal to n gamma n. Sorry. So it is a very important property here. You should remember this by heart. This no need to prove. I am proving this for you. The UPSC doesn't have any syllabus, defined syllabus. It could ask any question. Okay, so I am proving this for you, but this is one of the most important property of gamma function which you should know. Okay, so we know that gamma n is equal to 0 to infinity e to the power minus x, x to the power n minus 1 dx. So what would be gamma n plus 1? This would be, we'll replace n by n plus 1. So we get x to the power n plus 1 minus 1 dx. This is equal to 0 to infinity e to the power minus x, x to the power n dx. Okay, so now what we do next, we solve this integral, that is gamma n plus 1 is equal to, I write this again. Okay, so how do we solve this and how do we get the relation between gamma n plus 1 and gamma n? Clearly n here is the power of x, and we need to get gamma n plus 1 in the form of gamma n. So what do? We solve this using by parts, integration by parts, which you have learned in your intermediate level, that by parts. And now for taking by parts, we do this using by parts, and we'll consider this one as the first integral and this one with the second integral. Okay, so what do we do here? How do we do by parts? That is, we'll integrate e to the power minus x, that is, okay, and we'll leave this one minus integration over e to the power minus x upon minus 1 and differentiation of x to the power n. So we get n into x to the power n minus 1 dx. Okay, so we'll solve this. I'll solve this later. First we solve this one. What does this shows? This is 0 to infinity, sorry, this is 0 to infinity e to the power minus x, and this minus 1 and this minus becomes plus, and this is n and x to the power n minus 1 dx. Okay, so clearly what do we get here? This is the gamma function, this is the value of gamma n. So we can write here this as gamma n, and here we had gamma n plus 1. Okay, now we have to solve this. We have to solve this. Okay, so when we put 0 here, clearly for n greater than 0, x to the power n, if we put x equal to 0, we get the value 0. So we clearly know the lower value by lower limit. Okay, when we put the lower limit in this function, we get the value 0. What about the upper limit? So this would be limit x tends to infinity. We have to solve e to the power minus x upon minus 1 and x to the power n. Okay, we have shown that if we put 0 here, we get the value 0. What do we get if we put limit x tends to infinity? Okay, so I'll solve this limit for you all. Now clearly I'll solve this somewhere else here so that it makes very clear. Okay, I'll erase this one. So what do we have? We have limit x tends to infinity e to the power minus x, x to the power n. Now this is limit x tends to infinity x to the power n upon e to the power x. Okay, so now we can do is that we can use the Taylor's theorem or Maclaurin's theorem, and we'll expand e to the power x in the term of x, so that we could get the same numerator and denominator, which would be a polynomial in x, so that the limit is easily solved. Okay, so this is x to the power n, and using the Maclaurin's theorem or even the expansion of e to the power x using Maclaurin's or Taylor's theorem, we get 1 plus x square upon 2 factorial plus x cube upon 3 factorial dot dot dot. This will go on to infinity. Okay, so what do we get here? Limit x tends to, if we divide both sides by x to the power n, what do we get? We get 1 upon x to the power n plus 1 upon x to the power n minus 1 plus 1 upon 2 factorial x to the power n minus 2. Okay, so at here where one of the n plus 1 factorial, this will go on. So x to the power n when divided by n, this will we'll get 1 plus 1 upon n factorial, and the terms after this, we get x upon n plus 1 factorial plus x square upon n plus 2 factorial and so on. Okay. Now if we put the limit here, x tends to infinity, now these all terms will tend to 0. Okay, and this term will become infinity. So n infinity and infinity and so on infinity, and this is plus 1. So summation of infinity with any number is infinity. So we get limit x tends to infinity 1 upon infinity, and that is equal to 0. So we get the value of this limit to be 0. Yeah. So this is 0 plus n gamma n. So we get gamma n plus 1 is equal to n gamma n. Now this is a very important property. I would say that it is the most important property of gamma function, and you should all, I would say, memorize it, that gamma n plus 1 is equal to n gamma n. Now moving ahead, it shows that we have seen another property that says that gamma n plus 1 is equal to n factorial. Okay, in this case one should note that n here is a positive integer. For now we can consider that, because factorial values of half factorial or 1 by 2, 1 by 5 factorial is not known. It is known, but it is not at your level to be known. Okay, so gamma n plus 1, we have to prove that it is equal to n factorial. Okay, so earlier we have proved that gamma n plus 1 is equal to n gamma n. Okay, now this could also be written as gamma n into n minus 1 gamma n minus 1. Okay, this is nothing but if gamma n plus 1 is n gamma n, Okay, so gamma n would be n gamma n minus 1 gamma n minus 1. Okay, so moving ahead like this only, we get n minus 1 into n minus 2 gamma n minus 2. Okay, so moving in this similar fashion, at the end we get gamma n minus 1 n minus 2 dot 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 3 2 1 gamma 1, and we know that the value of gamma 1 is 1. We have proved this earlier only, that value of gamma 1 is 1. So what do we see here? This is the value of n factorial. Okay, so gamma n plus 1 is equal to n factorial. So if I say that what is the value of gamma 3, so you will write it 2 factorial, which is equal to 2, or gamma 5, this is equal to 4 factorial, which is equal to 24, or gamma 6, or any number, this is equal to 5 factorial, this is equal to 120. So gamma n plus 1 is equal to n factorial. You should remember that. Okay, it will help us to solve many of the I would say integral problems of sine, cos, and every of those function in the future. Moving ahead, what do we see here? Another property, it says that gamma n is equal to infinity if n is 0 or n is a negative integer. Okay, it says that for if we have taken that, one should note here that it is for negative integer, not for any negative number. Okay, for negative integer, that is gamma minus 1, gamma minus 2, gamma minus 3, gamma minus 4, this is all equal to 0, or gamma 0 is infinity. One should note that, not that every number negative integer, we can find the value of gamma minus 1 by 2. Okay, so how do we do this? Now, we know that gamma n plus 1 is equal to gamma n gamma n. Okay, so one can also write that gamma n is equal to n plus 1 upon n. Okay, so if we put the value 0 for n equal to 0, for n equal to 0, gamma 0 is equal to gamma 1 upon 0, this is equal to 1 upon 0, this is equal to infinity. Similarly, using that same formula, if we want to find the value of gamma minus 1, we get gamma minus 1 plus 1 upon minus 1, this is equal to gamma 0 upon minus 1, this is equal to infinity upon minus 1, this is equal to infinity. Okay, so any number for any negative integer, if we get the value, if we have this negative integer, we get the value infinity. Gamma n is equal to infinity for n equal to 0 and a negative. Now, one thing for your examination, see, we are here to clear this examination and not to do PhD in mathematics. This should be your utmost aim, to score maximum marks in mathematics optional, and not to get too attached in how to learn mathematics or to do PhD in mathematics. Okay, we are here to get maximum marks in mathematics. That should be our goal. So you should only know this. These questions, these properties are not there to be proved. Okay, moving ahead. Now, this is another important property, and this could come in your examination. And I think, I'm not sure, but it has been asked in the Indian Forest Service paper. Way back, it has been asked in the Indian Forest Service paper of Mathematics Optional. Okay, so you should know the proof of this, and you should by heart this, that gamma, value of gamma half is under root pi. Okay, so I'll try to prove this here. Now we are given that we know that gamma n is equal to 0 to infinity e to the power minus x, x to the power n minus 1 dx. Okay, so what would be gamma half? This would be 0 to infinity e to the power minus x, x to the power minus 1 by 2 dx. Okay, yeah, we get e to the power minus x for minus x and minus 1 by 2 dx. Moving ahead, if we put let's try this. If we put x equal to say u square, okay, so what do we get here? Dx equal to 2u du. If we put x equal to u square, so we get dx equal to du, or we could put x to the power dx u square minus u square x to the power minus 1 by 2. Okay, now this substitution won't work here. Okay, so we have to put x equal to e to the power minus we have to put x to the power minus 1 by 2. Okay, we put this as u. Okay, so what would be x to the power minus 1 would be u square. Okay, or x equal to u to the power minus 2. So dx would be, no, this won't work also. We put gamma half okay, we put here x equal to u square. Okay, so we get dx equal to 2u du. If we put that there, we get e to the power minus u square to the power minus 1 by 2 dx. Okay, so we get e to the power minus u, and if we take the change the limit also, for x equal to 0 u would be 0, and for x equal to infinity u would also be infinity. Okay, so we get e to the power minus u square, and this would be equal to u to the power minus 1 dx, and from here we can see that dx up into u to the power minus 1, this is equal to 2 du. Okay, this u comes here, so we get du. Okay, so we write here 0 to infinity e to the power minus u square, u to the power minus here, and we would write 2 du, or we get 0 to infinity e to the power minus u square 2 times du. Okay, so this is the value of gamma half. Similarly, we can also write that gamma half is also equal to 2 into 0 to infinity e to the power minus v square dv. By the properties of definite integrals, that doesn't matter if we change this variable, that is u to v. Okay, so what if we multiply these two? We get gamma value of gamma half whole square to be 4 times, okay, 0 to infinity e to the power minus u square plus v square du dv. Okay, yeah, we get this. Till now I think it is very clear. We have taken the, I would recap it for you. So we have taken gamma half to the 0 to infinity e to power minus x to the power minus 1 by 2 dx, and we have put x equal to u square. Then we get the integral 0 to infinity e to the power minus u square 2 du. Okay, and we have taken another this in the form of v, and we have written this like this. Okay, so what do we do here? If we change this into polar coordinates, what happens if we change it into polar coordinate? That is, if we have taken u is equal to r cos of angle theta and v is equal to r sin of angle theta, then du dv would be r d theta dr. Okay, so moving ahead, and this property you will learn in the calculus portion, where we use Jacobian to change the integral, change the variables in the integral, changing into polar form. Okay, and the limit would be here. I would solve it here only. The limit would be gamma 1 by 2 whole square is equal to 4 times e to the power minus, see, u square plus v square, u square plus v square, if you do u square plus v square, it will be r square. So it will be minus r square. Okay, and for du and d theta we put r d theta dr. Okay, and what would be the limit here? Now here the limit is from 0 to infinity, x is from, u is from 0 to infinity, and v is from 0 to infinity. Clearly it is the first coordinate. Okay, and if we change this into polar coordinates, see, the limit here for u and v, suppose this is u and this is v. Okay, the area of the integral would be 0 to infinity, u is from 0 to v, this area, this whole positive first quadrant is the area. Okay, now when we change this into polar coordinate, so what would be the limit? If you have taken this r d theta dr, a small element, so what would be the limit? R would vary from 0 to infinity, and theta would vary from 0 to pi by 2. Okay, so this would be theta is equal to 0 to pi by 2, and r is equal to 0 to infinity. Okay, solving ahead, 4 theta equal to 0 say pi by 2 d theta, and this is r equal to 0 to infinity e to power minus r square r d theta dr. Okay, so if we put r square to be t, I put it here in the rough work. Okay, rough. If we put r square equal to t, then we get 2r dr, 2r dr is equal to dt, or r dr to be dt upon 2, r dr to be dt upon 2. Okay, so this would be 4 zeros, theta is equal to 0 to pi by 2 d theta, and this would be e to the power, for r square equal to t if I is equal to 0, t equal to 0 and r equal to infinity, this is equal to infinity e to the power minus t dt upon 2, and from here we get pi by 2, this d theta 0 to, and this here we get e to the power minus t. If we integrate it, we get 1 by 2, this is equal to pi. So the square of gamma half is equal to pi. So what will be gamma half? Gamma half would be under root of pi. It has been proven here. Okay, so I'll recap this question for you, and this is a very important theorem which can come in your examination. I would not say theorem, it is basically a property. It is gamma 1 by 2 is equal to under root pi. Okay, so what did we do first? We first took the value of gamma n, which is 0 to infinity e to the power minus x to the power n minus 1 dx. And for gamma 1 by 2, it will be 0 to infinity e to the power minus x to the power minus 1 by 2 dx. And we put x is equal to u square. So we get dx equal to 2u du. And we get u inverse dx equal to 2 du. If we put this here, the value of x which we have taken, that is to be u square, we get e to the power minus u square to the power minus 1 dx, and u to inverse dx as we have got from here, it is t 2 times du. Now, so we get the value of gamma half is equal to 2 times 0 to infinity e to the power minus u square du. You should know this. This is in fact this is again a very important property. See, no one knows if we find the indefinite, there's a extra trick for you. No one knows the value of 0 to indefinite integral of e to the power minus x square. It hasn't been, no one can solve this. Okay, so if we are able to do this, so we could get the value of, if 0 to infinity e to the power minus u square du, we get gamma half upon half, that is equal to under root pi by 2. You should also remember this, that e to the power minus u square, sometimes you have to directly use this into question, that is under root pi upon 2 itself. This integral itself is not solvable. This integral itself is not solvable. E to the power minus u square is not solvable integral by any method. It cannot be solved. But see, I have told you earlier also that this gamma function and beta function, we could solve these integrals. We could solve this definite integral. See, the limit here is given 0 to infinity. If it would have given e to the power minus x square dx, we couldn't have solved this. If the limit, the definite integral, indefinite integral is not solvable here. But since it is given the 0 to infinity, we are able to solve this. Okay. So moving ahead, we have taken another value to be e to the power minus v square dv. And when we have product, we got the product here, which is equal to 4 into 0 to infinity e to the power minus u square plus v square du dv. Now next step, what we do, we change the from Cartesian product to polar coordinate system. That is, we have taken from u v to r theta. Okay, we have taken u is equal to r cos theta and v equal to r sin theta, and we get du dv is equal to r d theta dr. This is a very simple transformation in the integration, which you have learned also, and which you will learn in the calculus portion. Okay, so moving ahead, what we did that gamma half, we get the value to be theta is equal to 0 to pi by 2. See, the area of the integration that time du dv was this area, and if we convert this into polar coordinate r theta, the r would vary from 0 to infinity, this whole first coordinate, but the theta would vary from 0 to pi by 2. Okay, so we have taken theta is equal to 0 to pi by 2 and e to the power minus r squared, and solving this we got the value to be pi, and gamma half would be under root pi. Okay, so I think it's very clear to you, and it will help you to solve many of the different difficult integrals, definite integrals, which are sometimes even not convergent.